Try that. Yes, technical problems called the operator of the technology is silly. We've been going on talking
33 minutes.
We've been talking for 33 minutes, folks.
Let's go back to our original
So let's
slide.
go back to our original slide. We'll give you the brief tour.
Okay, now we're on the... Okay, so...
Oh, man, oh, man. I feel dumb. It was a simple oversight. I apologize, folks. I apologize, Wayne.
Okay,
I am
it's okay.
losing my mind.
Well, welcome to the Cosmic Pie Podcast. This is episode 31, season 3. In fact, we are about 34 minutes into the podcast and showing some wonderful slides. Yeah. Anyways, welcome. We're sorry for the technical issue. We do have a live chat that's running, so if you have any comments or questions you'd like to ask us throughout the podcast, please use that feature. Also, disclaimer, anything that Robert and I say, even though you may or may not hear it, is of our own doing and has nothing to do with the personal opinions of anybody else or any institution or whatever. Now, if you'd like to watch our podcasts, we do have them on Spotify the next day, so please feel free to to look at that. So, Robert, let's start things off.
Okay.
So the first thing we're going to talk about, the other one was just a dress rehearsal.
The other one was a 30-minute dress rehearsal, yeah.
So what's in the news lately has been the Comet, and we're going to say a little bit more about the Comet. In fact, there's still a lot of chirp I noticed on the internet about whether this is an alien spacecraft or not. So the thing is, it's the difference between what's possible and what's probable.
Right.
Now, it's possible this Comet is actually a Big Mac.
Or a left shoe Nike.
Or a toaster flying through space. But, of course, if you think of the difference between what's possible and what's probable, it's probably not a Big Bang. It's probably not a Nike flying through space. And it's probably not a toaster as well.
Right.
Chances are it's a comet, it's a comet, it's a comet. Now, the image that you see on the left side is green in color. That's the comet. Some people get all, worked up. Oh, my God, it's a green comet. And by the way, it's a UND green. You realize that?
I did. It's a Kelly green. Yeah.
So maybe it's a UND hockey puck that's going through space. It's possible.
It's possible.
Not probable, but it's possible.
Yeah.
Right? Anyways, so the green that we see here is due to what, Robert?
Cyanogens, CN ions.
And how prevalent is that in comets in general?
Quite common. Comet Holmes, Comet Halley, if I remember correctly, glows green at times. It's a common property because cyanogens are common chemicals in comets.
You remember the green person on Star Trek?
I do.
It was only a woman, wasn't it?
Well,
was there a guy there?
There are supposedly green Orion gentlemen as well, but all the Orions that were shown on Star Trek were female. So.
That's what I thought. Because back in the original series in the 60s, it was female, right? All green.
Yep.
Anyways, it's not one of those either. That's not responsible for the green color.
Right.
Okay, just so you know, in case someone's out there thinking about it. Now, the comet, one of the things people have noticed is the fact that it's a lot brighter than what is expected. And you see that on the plot on the right side. So on the plot on the right, we have two curves. One's a red curve, one's a blue dash line. And those are model predictions. They're two different models have different initial assumptions. That's why their predictions are a little different. On the vertical axis, we have magnitude. So it's like a logarithmic measurement of brightness.
Right.
And just so people know what this means, if you look at the difference in brightness, let's see, between the number 16 and 17, the smaller the numerical value, the brighter the object. And a difference of a factor of 1 is a difference of 2.5 times in brightness.
Right.
So if you were going to compare an object, let's say that was at 15th magnitude to 17th magnitude, that differs by 2 units. Then you take 2.5 multiplied by 2.5, and that would be the brightness difference. So if you're different by 5 units, that would work out to exactly 100 times difference in brightness, for example.
Okay.
Now, what's happening here is that you can see the blue crosses. Those represent observations. So on the horizontal axis on the bottom, the x-axis, if you like, is just date, so time. And if you look at earlier in time, so back in July, that's what you see on the leftmost side of the plot. And notice the scattering in the blue crosses. So that's just observations. Each have their uncertainty in their measurements. So that gives you an idea of sort of what is the expected uncertainty in the measurements of the observations that people were obtaining at that time. But as you make your way towards the right, going in the horizontal direction here, you'll notice all of a sudden the blue crosses start deviating away from the curves. They start to go up dramatically. In fact, the separation of the latest observations to the models is about a difference of about a factor of 40. So this comet is about 40 times brighter than what we'd expect based on the modeling.
Right.
But that's not unusual.
No. It's quite common. I will mention Comet Holmes again. It brightened up more than they were expecting, and then it disintegrated and dimmed real rapidly. So these things happen. Comets get brighter. They brighten faster than we expected. They dim faster than we expected. So yeah, this is not something that's really that unusual.
And the neat thing about the comet is that we know from observations done of its position with time that it's on a path that has taken it from outside the solar system, making it will make a close approach to our sun, and then it'll go back outside the solar system. So it's not in a bound orbit to our sun.
Right.
There's no doubt about that.
Right. There really isn't. I mean, we're calling it a comet, and people may think, oh, you're saying it comes from within the solar system. No. It definitely did not originate in the solar system. But it's still behaving like a comet.
And because of that, this could be the first passage of the object close to a star.
Mm-hmm.
And when that happens, you have like fresh supply of material on the surface of this comet that gets energized by the photons from the sun, like ultraviolet light,
Right.
and causing the material then to emit light. This is what we're seeing in the light that's coming from the comet itself. And so maybe it's not that unexpected because this is highly unpredictable. There have been many comets in the past that astronomers said, oh, it's going to be extremely bright. It's 3 times brighter than the full moon when it makes its closest approach to the Earth, in a year and a half from now. And it doesn't even get close to that.
Right.
In fact, astronomers have learned, at least most of us, that you don't make those type of predictions because, there's a chance you're going to have pie in your face.
Right.
So you don't want to do that. So it's not unusual that this comet has brightened up more significantly than what we expected. That is really the nature of comet. In fact, this actually makes it more of a comet than anything else. It was an alien spacecraft that kind of came inbound to our solar system and is camouflaged to pretend it's a comet. Why would it do this? You'd think it would follow sort of the natural predictions, that cometary bodies follow on average. So in that sense, this is not out of the norm.
Right.
But it's possible it could be. No, just kidding. So let's move on. Yeah, and the other thing that has happened recently is that we've gone through these series where the shadow of Titan then can be seen on the surface of Saturn. So this started back in July, and this sort of sequence of transits, as we say, happens every 15 years or so. Now, I've looked for these, and unfortunately around here the weather has not cooperated. It's either been cloudy completely or it's been really hazy, and it's not been very good for observing.
Humidity's been real high.
And it's only on these just a few times, roughly since July that this occurs. Now, one that's recently occurred was back on the 20th of September. So this is an image then taken of that. You can see in the top Titan shadow and the Titan going across Saturn itself.
Mm-hmm.
Now, the next one will take place on October the 6th at 12:32 a.m. Central Daylight Time. That will be the beginning of the shadow moving across the surface of Saturn. It usually lasts for a few hours. Mm-hmm. So if it's a little bit cloudy, you can kind of wait it out a little bit, and hopefully that it clears and go like that. But hopefully you'll have good luck. And if not, you got to wait for 15 more years. So you better eat a little healthier if you're old like us, and hope that you're still around 15 years from now to be able to make those observations. So hopefully October 6th will be the time to do those observations.
Okay.
Now, the other interesting thing, which is kind of where we started for most of you, for all of you, I guess, except Robert and I.
Yeah, this is where we were.
So we were talking about the latest paper that's been published based on observations taken of the merging black holes and their release of gravitational waves. So just to kind of summarize all this, back in 2015, for the very first time, we detected gravitational waves using the LIGO experiment, which stands for Laser Interferometer Gravitational Wave Observatory. There are 2 facilities at the time. There are several more now that's come online since. One of them is in Louisiana, the other in Washington State. And how they worked is that the general theory of relativity, one of the predictions that come from it, is that there should be gravitational waves, and you can think of them as undulations in the fabric of space-time, that these gravitational waves should be released when we have, for example, the merging of asymmetric black holes. That means black holes that don't have identical masses. And what you get in that fact is that some of the mass, when these black holes merge together, some of the mass goes into essentially the energy of the motion, the movement of space itself. Right. Now, space itself is extremely stiff. Yeah, so it takes a lot of energy, i.e. mass, to make it shake. But if you have the right equipment, you can detect that shaking. And what happens is space itself, when a gravitational wave washes by you, space itself then stretches ever so slightly in one direction and then squeezes ever so slightly in another direction, perpendicular to the first direction. And on average, when we look at different systems that are responsible for the release of gravitational waves, you'd expect that the disturbance of space, the stretching and squeezing, is on the order of about like 10,000th the size of a proton. So in other words, it's completely negligible and we never have to worry about that.
Right. But, people go, well, how can we measure something like that? Well, this is why the arms of LIGO are 4 kilometers long. And as to the sensitivity of an interferometer, which is what this thing uses, we've built one up in the second floor of this building. And we noticed and laughed about it while we were putting the thing together and testing it. You could see shifts in the pattern of the fringes, as they're called, the sequences of light and dark lines from our breathing. So just somebody breathing in the room was able to produce shifts in these fringes that they're looking for.
So don't burp because you'll ruin your experiment.
There you go.
Now, how this device works is you can think of an owl-shaped object, and these are 2 long arms. Each of the arms are 4 kilometers in length. They're an evacuated tunnel. You think of it that way. And what you do is you shine laser light down these 2 tunnels. They're perpendicular to each other, hence the L shape. And the light gets to the end of the tunnel, bounces off of a mirror, and then the light comes back to where the source of the light is. And at that point, you have that light combined. Now, if you think of a classical wave, for example, the up and down oscillatory type of motion, like a sine wave, for example, what happens if the light that comes back and gets recombined, if the light's in phase with each other, perfectly in phase, right, then you're going to get a double the amplitude, double the height of the peak or the crest, and double the depth of the trough. But if you tune things in such a way that the wave is completely out of phase with each other, that means when one wave is at the peak, you can think of the other wave as at the trough. And when they add together in such a way to give you nothing. Right. So you can tune things in such a way that when light then, when it comes back up now, in practice is much more complicated. The laser light gets bounced back and forth thousands of times and so on and so forth. So we're keeping it very simple of just a demonstration here. That you can tune things so that when light reflects off the mirror and comes back to the light source, they combine in such a way to give you nothing. And all you need then is some type of photocell in a computer that's monitoring a certain space, a certain area, looking for the appearance of light. And if you see a flash of light, that would signify that a disturbance has occurred, that the path lengths have been changed ever so slightly, so then when the light did combine, it was no longer perfectly out of phase, and therefore you'd see some light.
Right.
And disturbances, and you can think of a lot of earthly disturbances like...
The truck going by a mile or 2 away, birds pecking on the building, kangaroos hopping through the field near you.
Is Louisiana?
No. I just we got into telling stories.
Now you're building one in Australia.
We were telling stories once about an interferometer that's in Australia, and it was dubbed the best kangaroo detector in the country.
Oh, I see, right.
So
Earth tremors.
right, so
Minor
earth tremors,
quakes.
minor quakes, all of this stuff plays a role.
So it really took up until 2015 where engineers had developed a technology to the point where it was completely isolated from most earthly things. So it was sensitive enough then for that slight change in path length that was created by gravitational waves. Now, to make sure that it wasn't a false detection, when a gravitational wave source is detected, let's say in this case for the very first one, it was detected first in Louisiana. A very short time later, it was also detected in Washington State. Now, gravitational waves travel at the speed of light, and you can calculate then what is the path length going from Louisiana State to Washington State. How long would it take something? It will pass right through the Earth as if the Earth's not even there. How long traveling speed of light would it take you to go that journey? Right. And that's exactly what they detected, that there was a slight delay from one detector versus the other, exactly what you would expect for a gravitational wave traveling at the speed of light.
And the waveform was the same, and
that's shown on the right side, the graphic there. You can see the undulation motion of the wave, and what's happening is the two black holes lose energy as they release gravitational waves, and they compensate by getting a little closer together.
So they spiral in.
So they spiral in, and after a time they spiral in, they get closer, 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 and all of a sudden, whoop, they merge together. And you get this burst of gravitational waves at the merger. And that is what you see as the final up and down, the maximum up and down motion of that plot there that you see on the right hand, sort of in the middle on the right hand side. And then things settle right out because then you form one black hole.
Aren't there even audio files of these
Yes.
waveforms that somebody put together, converted what they would sound like?
Yeah, LIGO did that. They call it the chirp.
Right.
So you can hear that sudden increase in frequency when these things, and it sounds just like that. It sounds sort of like a, bloop, bloop, just like, and they slow it down for that, but it's really fast.
It's fast.
It's like bloop, bloop, like that. These are these black holes that are merging together, type of thing. So, what's this paper is all about is that people at a team have done detailed analysis of the waveform, the gravitational waves that are released during the merging process. And what they discovered is that black holes are actually very simple beasts macroscopically. We know three parameters that describe black holes. They're their mass, their spin, and their electric charge. And we expect that most black holes would be electrically neutral.
Because they would absorb enough matter and energy that they would balance.
Yeah, the charges would balance in the material that ultimately falling into the black hole itself. And so we'd expect, therefore, that it's mainly the mass and the spin or angular momentum that are two fundamental properties. And that's exactly what you see if you assume black holes only had those properties. That's the type of waveform that was detected in these really, if you like, high-resolution examination of the gravitational waves. And the other thing, and that's supported here, and that's known as the Kerr theorem. So Kerr was the one that proposed these ideas. The other one is one from Hawking called the area law. And what it says, if you take the surface area, think of the event horizon of a black hole, the point of no return. And by the way, a black hole, in case you don't know, is an area where space has curved in such an extreme that it's curved in on itself. And the analogy I always like to use is imagine an ant trapped inside of a paper bag. It doesn't matter which direction the ant travels or crawls in, it's never going to get outside that paper bag. Now, for that, think of light trapped inside this collapsed region of space where light can't get out. In fact, no information can get outside of the black hole.
Right.
That's kind of what's going on here. And so what Hawking suggested was that the surface area of the event horizon, that point of no return, then that area, if you take two black holes and merge them together, that area would never decrease. It would only increase. And it's related to something in thermodynamics that we call entropy. So you think of the different possible states that something could be in. For example, if you had an evacuated cube and you release some gas in one corner of that cube, that gas would naturally diffuse through that whole volume and spread throughout that cube. So so initially it's all in one corner. So there's not many places you can go to be in one corner of a room.
Right.
Right? You only have a few choices that you can make. So the entropy is extremely low. But as that gas spreads out, there can be many microstates that gas can be in. And so the amount of entropy increases with time. Yep. So this is a fundamental law, second law of thermodynamics. So this area law that Hawking proposed then is related to the entropy of a black hole. And if a black hole has entropy, it must also have a temperature. And that temperature is related to the Hawking radiation. Now, we should do a whole podcast on that someday, because we certainly don't have time today to do that because of what has been going on.
Yeah.
So the analysis then of this binary black hole merger that's taken place through the release of gravitational waves then has shown that both of these ideas seem to be correct, both the Kerr theorem and the Hawking area law. So it's very interesting that you can actually show that it's consistent with that, given that these are very difficult type of things or measurements to make.
Right.
Now, speaking about black holes, an announcement was made not too long ago. In fact, the paper you can see there on the left side, it's not even finalized. It's still under peer review and so on, and then being looked at. And it's from the Event Horizon Telescope people. These are the ones that observe the black hole shadow for the first time, both at M87, which has a black hole of about 6 million times the mass of our sun, and the one in the center of our own galaxy, which have a mass of about 4 million times the mass of our sun, to show that black holes do indeed exist. Here they are.
Yep.
And the only reason you can see the black holes, by their very nature, light can't escape from within them, is that there's material outside of the event horizon in the vicinity of the black hole, and that material gets heated up like through friction, you can think of it that way, and emits light. And so that's the light that you see. Now, the space around the black hole is highly distorted. Think of the nature that space curves in on itself. It's not flat space. It's highly distorted. And so you get these weird optical effects where you see the ring around the black hole, which is really seeing the other side of the accretion disk that normally you can't see, because it's like a funhouse mirror at a fair or something.
That's
right?
a good way of looking at it.
Yeah, it's similar to that kind of stuff that's going on. Anyways, they had been measuring and watching then these black holes with this telescope, which is a combination of signals from multiple radio telescopes and adding more to it all the time from across the world. And what they discovered was that the polarization has flipped in the black hole that's in the center of M87. Now, this galaxy is about 55 million light years away. And by noticing that it has flipped then, that gives us information about the magnetic fields in that material that's outside the event horizon of this black hole.
So it's not the magnetic field of the black hole, it's the magnetic field of the material around it.
Yes, and so the polarization has changed.
That's neat. That is really neat.
Never seen before. Of course, we didn't have these type of observations until fairly recently that we can make the... Black holes can see. They just see at a different wavelength. They don't see like our eyes, but you can reconstruct images taken only in, using radio photons, so that they do see in that sense.
Yeah.
Just like
our
eyes
it's still
can
electromagnetic radiation, whether it's radio waves or visible light or X-rays.
Bumblebees see in ultraviolet.
Right. We can't.
No.
But they can.
You can a little.
But
Bumblebees, they can't. So the next thing I want to mention is we now mark 30 years since the first exoplanets have been found, planets going around other stars. And the tally now has hit over 6,000.
Wow. I remember when they were crowing about it being 3,000, and now it's 6,000. And such a variety. Everything from Jupiter-sized objects, the planets that are in close to their star, to super-Earths, which are 2 to 5 times Earth mass, but almost certainly rocky because of the density. Because if they transit, we can get their volume and mass from different ways. But usually you got to have two pieces of information. You got to have radio velocity information and the transit to get the mass. Anyway, that's a whole nother show in and of itself.
Well, prior to the discovery, in the mid-1990s, with the first exoplanets around a pulsar neutron star, was the very first ones that were found. 51 Pegasi was the first ones around a sun-like star.
Right.
So there's a distinction there. But either way, because we have this sort of numbers now, we can make some good statistical arguments that on average, every star,
has a planet.
every star has a planet.
Right.
Which we really couldn't make prior to, the mid-1990s. So this science has come a long ways. Now, the other thing that's interesting is that out of these 6,000 plus exoplanets, none of them are like the Earth.
None of them. Yeah.
None of them.
Not yet.
None of them. But 6,000
Yeah.
It seems like a large number. In fact, if you give me $6,000, I won't hesitate to say thank you and
Right.
quickly stuff it in my right pocket. But when we look at stars, there could be up to 4 billion stars in our Milky Way. If each of them have a planet, at least one, that's 400 billion planets in just the Milky Way. And there's like 1 trillion galaxies in the observable universe. Could there be one planet out of that huge number that would be like the Earth?
Probably.
There's got to be.
I would give
It's
that high
possible, Robert.
Yeah. I would give it a high probability, just random chances says you're going to get something like Earth.
In other words, the number seems very large to us, 6,000. Like I said, if it's in dollars, it's,
Yeah.
But when you think about the number of stars in our galaxy, it's a really small number. So we barely scratch the surface, as we like to say on this type of
where this
observations.
statistics is coming in, it has to do with the fact that we can only see the very small region around us because gas and dust start blocking visible light and even X-rays and gamma rays and so forth.
And the question is, do you need an Earth to have life?
Right.
Well, one of the things we like to look at is planets in our own solar system like
Mars.
Mars. Now, what was the big thing that was announced about Mars recently?
Well, they found 2 iron-based minerals in conjunction with each other. Both of these minerals can be produced by life, but they can also both be produced by abiotically, in other words, by other processes in life. But when you have the two together, because the processes that form them that are abiotic don't tend to happen in the same location. So I did some poking at this. They can, but it starts becoming increasingly unlikely that with those two together, that it was an abiotic process. So that's kind of neat. Is it? So they've proven life was on Mars? No, but it starts becoming intriguing.
And you know what we need to do, don't you?
Well, we need more rovers.
Well, we need to go to,
Oh, okay, yeah.
in some way, either using robots or humans, we need to go to Mars and bring back the samples.
Right.
So we can put them in our very advanced laboratories that we have here on Earth and actually do the type of measurements that would show us whether or not it's actually biology at work or it's not, or some type of chemical processes that's going on and responsible for what we observe.
And I like this because we've commented on this before with other exoplanet and, discussions on how do you find what is a definite signature of life. This gets into what I like to think, which is there is no one thing. But when you start combining all these things and seeing multiple avenues of chemicals that life produces, now you're starting to talk. Now you're starting to narrow down those other possibilities.
So it's that looks like a duck, walks like a duck, quacks like a duck type of idea?
That's kind of it. Yeah, these two together, that's interesting. If there were 2 or 3 more that are produced by life that are in this location, now we're starting to see something. And that's where I'll agree with you. We want sample return so we can see if maybe in minute quantities these other biotically produced minerals are there.
Now, if you want to explore the surface of a body, the easiest one to get to first, of course, which we have done, historically, is obviously the moon.
Is the moon.
Now, do you know what the phoenix is?
It's a bird that bursts into flame and consumes itself and then is reborn from the ashes.
And that's exactly what's happening here with the Viper rover. The Viper was canceled not that long ago, a little over a year ago, even though they had spent over $400 million constructing the thing, designed to land in the South Pole region of the moon and look for evidence of
Water.
So ice. Because we would expect water to be in liquid form, of course.
Absolutely.
On the surface.
Yeah. Okay.
Right? Now, so you can see Viper, which stands for Volatiles Investigating Polar Explorer Rover. I'm glad we call it Viper.
Yeah.
It was canceled, but NASA has recently brought it back. So it is the Phoenix in that sense. And the idea is that Blue Origin is actually going to launch Viper to the moon. So we expect this to happen in late 2027. So at least we didn't build something, spend almost $500 million on it, and then throw it in the trash can or surplus it or whatever, that we're actually now going to use it and launch it to where it was supposed to go, that is to the moon itself. And this is just the ongoing battle to get back to the moon, to look at some really interesting features like in the polar regions.
Right.
So to see if there is water ice in the permanently shadowed craters.
Mm-hmm.
It's possible.
Or even just underneath the regolith.
Yeah, or underneath the soil a little bit.
Yeah.
And either way, the moon is so convenient. It's only a few days travel away from us. And Mars, of course, is months and months and months with our present technology. And so if we're going to finally explore the rest of the solar system with humans for good, then, of course, the moon should be the first stop. It makes logical sense that that's the case. Now, in that whole process of doing that, we have the Artemis project, where we're going back to the moon. So late next year, we're going to send Artemis 2 around the moon, like the Apollo 8 back in 1968. So we're kind of redoing things. Part of the reason for that is we don't have a lander to get to the surface of the moon. We have a rocket to get us to the moon. So that's the SLS. So if you like, it's doing the job of the Saturn V did in the 60s and 70s.
And the first time in a long time, we've put together a rocket that was even remotely powerful enough. So,
and we've sent the Orion space capsule and around the moon and stuff in deep space and back again, so beyond the moon and back. I had some issues. There's the problems with the heat shield that hopefully they work out, because that was unmanned. The next launch is going to be manned. It's going to be 4 astronauts on board. And the other thing is the environmental control system wasn't installed or working on the first launch because there was no people on board that needed oxygen and water and everything to stay alive. So this is the first, if you like, true test of the environmental control system. So hopefully that works.
Yeah.
In some sense, like they did in the Apollo program, maybe we should have just put it in orbit around the Earth, give it a shakeout for a few days, then re-entered, and then the next flight send people that far away to the moon.
Yeah.
But anyways, I don't make those decisions.
It would be reasonable.
But even, and this is the case, let's say that the second Artemis 2 comes out without a hitch, no problems at all, right? Everything works like it should work. You still can't get to the moon. And you can't get to the moon because, as I mentioned, we don't have a lander to go from lunar orbit to the surface and back again. And the hope is that SpaceX will provide that lander. So that's one of the motivations.
Isn't Blue Origin also
Yeah, well, I'm going to get to that. So the initial contract was given to SpaceX to build a Starship, essentially, that ultimately would land on the moon and back up into lunar orbit again. The main goal of SpaceX, so as Elon Musk has stated, is to get to Mars. So he wants to send these things off to Mars. But at least you're going to get some money and help with the development by, manufacturing a lander for the moon itself. But that's not available yet. Okay. But then later on, Blue Origin was also given, there were some legal battles that happened in court and so on and so forth. So NASA decided to give Blue Origin a contract to develop a lander. I haven't seen anything with that.
I haven't either.
They had this initial lander before the contract was initially awarded to SpaceX. That Blue Origin had a lander, a demonstration. It looked kind of cool and interesting. It was like an enhanced or glorified lunar module back in the Apollo project days. But it looked like it could easily work. SpaceX is Starship. I'm not so sure of that, the way it lands and so if that's really going to be developed in time. And there is a time. The clock is ticking because the United States wants to get back to the moon before another country that is well underway of developing their equipment. In fact, they tested their lander this past summer, and we've spoke that on the previous podcast. So we're in competition again, even though we beat all other countries to the moon and landed people on there in '69. It seems like we're back in competition again. And I think the idea is that when we go back to the moon, it's almost going to be like a base in Antarctica, that we're going to stay there. But this time, where you land, that's your territory. It's kind of seems to be like that. So if you have some other country lands in the South Pole region of the moon, they might claim that territory.
Right.
And if that's where we find good resources like water, That's going to be a big benefit then of not having to haul that stuff from the Earth to the moon. It's already there in situ and be able to process it on the lunar surface. Now, so it's important for countries to get to the moon now first in this more modern time. So it's not clear to me that SpaceX's Starship development is going to be on time to be able to get there before essentially 2030, 2031, where this other country is supposed to land on the moon according to their schedule. Now, I'm not the only one, of course, that is worried about this. This is an article that has been published recently in the New York Times, and it's by Eric Lipton, and the title is U.S. is losing race to return to moon, critics say, pointing at SpaceX. And it's all based on the fact is we do not have a lunar module equivalent, something that we can land on the moon with. So this, as we've talked about this ourselves, both on the podcast and personally towards with each other, that this can be a real hiccup to this whole Artemis project and getting back to the moon in a timely fashion. That's the important word, timely, fashion here.
Because you can take your time and get there anytime you want.
Yeah.
But if other people are trying to get there, it might behoove you to get there first.
In fact, there has been so much new things that have to be engineering problems that had to be fixed, if you like, to go to the moon on this lander through the means of the Starship itself. Maybe that wasn't the smart way of doing it. We should have kept doing what we're doing with Starship and SpaceX, but maybe developed something else that would get there quicker.
Right.
But not necessarily better, and the fact that it wouldn't carry as much payload to the lunar surface and so on. Right. But then we can replace that later on with a new type of vehicle, maybe developed by Blue Origin and SpaceX.
I would argue this is what we did in the 60s to do what we did, is we put out calls and said, hey, we need this, and companies came up with the idea. Not a company, but several companies tried bidding on various parts of the process. So here we put our eggs in 2 baskets, and we're wondering why we're coming up short. Doesn't surprise me at all.
Yeah, so that's going to be something to look for. And these time windows are getting really narrow, because here we are in late 25. So if we're going to get there in 2030 and land people on the moon, we have 5 years, less than 5 years to go, right? You have about 4 years roughly.
Done. We've done it, but
we'll see. And you need the support and you need the money. That's the important thing to really push things. So we'll see how this plays out. But people are starting to get anxious about this.
NASA budget in the 1960s was 10%. Now it's less than 1%.
Yeah.
So
we'll see how all that plays out. But if you want to get involved in these kind of exciting things, of course, you can go to higher educational institutions like our own here at the University of North Dakota.
Right.
We have both on-campus courses that you can take or online courses and various degree programs of all walks of life.
Right.
It's a very beautiful campus. There's a lot of stuff happening. We have a new STEM building that's being constructed, So it's a real, a lot of stuff going on.
A lot of stuff going on.
Yeah, and a lot of interesting things and a lot of development. So it's well worth checking out. Even if you're not going to university or plan to go back to university, come by for a visit.
Right.
Check it out.
We'd be happy to see you.
Check it out.
Wow, what's going on with my camera? Oh, well. All sorts of weird things going on today.
Technical problems. And our next podcast, hopefully you'll start on time.
Yeah.
Sorry, Robert. Will be next Tuesday on September the 30th. And we always leave you with a quote at the end. And this quote is by Wernher von Braun.
Von Braun.
And we talked about the moon landing. He was instrumental in the Apollo program, of course. So here's his quote. By the year 2000, we will undoubtedly have a sizable operation on the moon. We will have achieved a manned Mars landing, and it is entirely possible we would have flown with men to the outer planets. Sigh.
Yeah. Like I said, that 10% down to 0.8%. Yeah.
That's the ramification of that.
That's the ramifications.
Anyways, if you like the shortened podcast, please give us a thumbs up. Smash that like button. Subscribe if you haven't subscribed. And we'll see you next time. Thank you.
Next time, folks. We'll get it right.